In today's video, we're going to go over the Black-Scholes PDE derivation. Now, the Black-Scholes PDE is one of the most famous equations in the world of finance. And many people look at it and they understand it, whereas others are left very confused. Now, as complicated as it looks, what we're going to do in today's lecture is we're going to derive it with simple Taylor expansion and multivariable calculus, without using Lito's lemma, which is a more advanced topic. And we're going to show that, in fact, the Black-Scholes model isn't as complicated as it seems, and that it's simply a limit as the time period approaches zero of a binomial model. So we're going to get started. Now, the starting point for our presentation is going to be trying to understand the binomial model. Now, the binomial model says that the call price today can have two possible futures. Now, with risk neutral probability P, it's going to go up, in which case the stock price is going to be multiplied by a factor greater than 1. And with possibility 1 minus P, the stock price is going to go down, in which case it'll be multiplied with a factor less than 1, which we call D. And using the stock price in either scenario, we can determine the call price in either scenario. And discounting that back to today, we will get the fair price for the option today, repeating this as many times as there are periods, we will get the fair price for the option. So that is the binomial model. Now, the first step to determining the Black-Scholes PDE is to simply multiply both sides by the risk-free rate. From there, we can get this equation. RC is equal to PC of this possible call price in this possible future plus 1 minus P of this possible call price in this possible future. Now, the only thing that we have to do is to determine what P is and what R is, and also what C is in each case. Simply plug them in, simplify, cancel some terms, and we realize that we will end up with the PDE for Black-Scholes. So how do we determine these variables? How do we determine P, C, and R? Well, the first thing that we can do is we can create a model in which the log returns can follow a movement that includes two components. It can go in a certain direction, which we call drift, and it can have a standard deviation that is random. Combining these two components, we can see that the price generally follows a constant drift term as seen in both the log up and log down components, as well as this drift component that differs between the two. Now, what we realize is that as delta, which is the length of our time period, approaches zero, both of these will become only having the square root of delta sigma term, and it'll not have the m delta term. So what this means is that the limit as delta, which is the length of a time period, approaches zero, the only term that we're going to have is this and this. And substituting x for square root of delta, we can see that ln of up simply becomes x sigma, and ln of down simply becomes minus x sigma. And what we can do from here is use the Taylor expansion for e to the x, right? E to the x is equal to the infinite series of 1 plus x squared over 2, and so on. And we can use this expansion to write out u, d, and r. Now, what are each of these, right? U is simply how much our stock price gets multiplied by in the up case. D is simply how much our stock gets multiplied to in the down case. And R is simply the risk-free rate. Now, using the risk-neutral probability equation, which says that P is equal to the ratio between R minus D and U minus D, and plugging in our results for U, D, and R, we can get that the numerator is this, the denominator is this, and doing some simplifications, we can show that the risk-neutral probability can be given by this expression, which is slightly deviated from 1/2. Now, using this, we can plug that into this equation. So at this point, we have already determined what P is and what R is from this, simply using the equation for risk-neutral probability and Taylor expansion. Now what we have to do is determine what the call price would be in the up case and the down case, plug them in, and determine the PDE for Black-Scholes. And that is exactly what we're going to do. Now, the way that we're going to determine the call price in the up case and the down case is we're first going to assign the up case call price to be f of x. Now, what this means is that we can effectively use Taylor expansion to expand this around x equals 0, right? Because we are using the limit as delta approaches 0, and recall that x is simply the square root of delta. So as delta approaches 0, x also approaches 0. Now, once we represent this in terms of f, we can use multivariable calculus to determine the derivative of f, which is this expression, as well as the derivative, or rather the second derivative of f. From here, since we know that the Taylor expansion is simply equal to f of x is equal to f of 0 plus f of, or rather f prime of 0 times x plus 1/2 f double prime of 0 times x squared, we can plug our results for f prime and f double prime into our expression for Taylor expansion, which these are just the intermediate steps for determining f double prime, evaluating it at 0, and plugging them in. We can see that f double prime is given by this expression, which is the second derivative of the call price with respect to stock price times the square of the stock price times sigma squared, plus the first derivative of the call price with respect to the stock price times the stock price times sigma squared, plus 2 times the first derivative of the call price with respect to time. So that is the second derivative. The first derivative is the first derivative evaluated at 0 is the derivative of the stock price, or rather the derivative of the call price with respect to the stock price times the stock price times sigma, and the f evaluated at 0 is simply c. Okay, so once we know all of these results, what we can simply do is plug that into the Taylor series expansion for f of x, right? And abbreviate each of these terms as C, A, B respectively, and we have the call price for the up case. Now we can similarly show that the call price for the down case has a similar form, but here instead of C plus AX plus BX squared, we have C minus AX plus BX squared. So using these abbreviations, we now have each unknown variable in our original binomial model. So we know what R is, we know what C is, we know what P is, and now we have just determined what C of SU T plus delta is and what C of SD T plus delta is. Okay, so now all we have to do is plug each of those into our function and realize that this is the expression we end up with after cancellation. So there's going to be some algebra here, but it'll be very simple and doesn't require any time series knowledge or advanced mathematical tools. Okay, so once we end up with this expression, we can simply recall that we substituted this term for A and substituted this term for B. So simply plugging A and B back in, we can realize that we end up with this expression. Okay, now canceling C on both sides, dividing by x squared, which is a common term on both sides, and expanding the fact that we substituted alpha as this term, we can see that we end up having the Black-Scholes PDE. Okay, so this is pretty much the derivation here. And finally, what we want to understand here from the Black-Scholes PDE is that what is this expression saying? Right, it's saying that the first derivative of the call price with respect to the stock price times the risk-free rate plus 1/2 of the second derivative of the call price with respect to stock price times s squared sigma squared plus the first derivative of call price with respect to time is going to be equal to the call price times the risk-free rate. Okay, and this is another form that we can write it. So all we have done in this video is effectively derive the Black-Scholes PDE using nothing but a simple understanding of the binomial model, the risk-neutral probabilities, as well as some multivariable calculus and Taylor expansion. So that's it for today's video. Please like and subscribe, and I will see you in the next one.